Hello, this is Chupak Lalit Prem Gajavelli from IARE, roll number 22951 A6216, branch CSE Cybersecurity, section A. And today's topic for Tech Talks is in linear algebra and calculus. The topic is SCHUR complements of M-MATRICES. So let us start the presentation. Firstly, let us look at the content. M-matrix. It consists of characterizations, equivalences, and applications. Next, SCHUR complements. It consists of backgrounds, properties, application to solving linear equations, and also application to probability theory and statistics, conditions for positive definitiveness and semi-definiteness. So firstly, let us start with the definition of M-matrix. In mathematics, especially in linear algebra, an M-matrix is a Z-matrix with eigenvalues whose real parts are non-negative. The set of non-singular M-matrices are a subset of the class P matrices and also of the class inverse positive matrices, which are the matrices with inverses belonging to the class of positive matrices. The name M-matrix was seemingly originally chosen by Alexander Ostrowski in reference to Hermann Minkowski, who proved that if a Z-matrix has all of its row sums positive, then the determinant of that matrix is positive. Next, characterizations. Definition. Let A be a n into n and with n rows and n columns real Z matrix, that is A equal to A ij, where I and j are rows and columns respectively, where A ij is less than or equal to 0 for all values of I is not equal to j, 1 is less than or equal to I, and j is less than or equal to n. Then matrix A is also an M matrix if it can be expressed in the form A equal to SL minus B, where B equal to B ij, where ij are rows and columns respectively again, and B ij is greater than or equal to 0 for all values of 1 which is less than or equal to I, j less than or equal to n, where S is at least as large as the maximum amount of moduli of the eigenvalues of B, and I is an identity matrix. For the non-singularity of A, according to the Perron-Frobenius theorem, it must be the case that S is greater than the rank of second matrix. Also, for a non-singular M matrix, the diagonal elements of Aij of A must be positive. Here we will further characterize only the class of non-singular M matrices. Many statements that are equivalent to the definition of non-singular M matrices are known, and any of these statements can serve as a starting definition of a non-singular M matrix. For example, Clement's list contains of 40 such equivalences. Now, these characterizations has been categorized by the Plemons in terms of their relations to the properties of the given things, which are positivity of principal minus, inverse positivity and splittings, stability and semi-positivity and diagonal dominance. It makes sense to categorize the properties in this way because the statements within a particular group are related to each other even when a matrix A is an arbitrary matrix and not necessarily a Z matrix. Here we mention a few characterizations from each category. Equivalences. Let A be a n into n where n and n are rows and columns equal real Z matrix, then the following statements are equivalent to A being a non-singular M matrix. A. Positivity of principal minus. All the principal minus of A are positive. That is, the determinant of each submatrix of A obtained by deleting a set, possibly empty, of corresponding rows and columns of A is positive. A plus D is non-singular for each non-negative diagonal value of matrix D. Every real eigenvalue of A is positive. All the leading principal minus of A are positive. There exists lower and upper triangular matrices L and U respectively with each positive diagonals such that A equal to Lu. B. Inverse positivity and splittings. This says that A is inversely positive, that is A inverse is greater than or equal to 0. A is monotone, that is Ax is greater than or equal to 0 implies that x is greater than or equal to 0. A has a convergent regular splitting, that is A has a representation A equal to m minus n, where m inverse is greater than or equal to 0, also n is greater than or equal to 0, with m inverse into n which is convergent, that is the rank of m inverse into negative and n is less than 1. There exists inverse positive matrices m1 and m2 with m1 less than or equal to A less than or equal to m2. Every regular splitting of A is convergent. Let's talk about C, stability. There exists a positive diagonal matrix D such that AD plus DA power T is positively definite. A is positive stable, that is the real part of each eigenvalue of A is positive. There exists a symmetric positive definite matrix W such that AW plus WA transpose is positively definite. A plus I is non-singular and G equal to A plus I power minus 1 into A minus I, which is convergent. Now A plus I is also singular, and for the value of G equal to A plus 1 power minus 1 into A minus I, there exists a positively definite symmetric matrix W such that W minus G power G transpose into W into G is definitely positive. Next, D, semi-positivity and diagonal dominance. A is semi-positive, that is there exists x greater than 0 with Ax greater than 0. There exists x greater than or equal to 0 with Ax greater than 0. Also there exists a positive diagonal matrix D such that AD has all positive row sums. A has all positive diagonal elements and there exists a positive diagonal matrix D such that AD is strictly diagonally dominant. A has all positive diagonal elements where there exists a positive diagonal matrix D such that D inverse into AD is strictly diagonally dominant. Next comes applications. The primary contributions to M-matrix theory has mainly come from the mathematicians and economists. M-matrices are used in mathematics to establish bounds on eigenvalues and on the establishment of convergence criteria for iterative methods for the solution of large sparse systems of linear equations. M-matrices arise naturally in some discretizations of differential operators such as the Laplacian and as such are well studied in scientific computing. M-matrices also occur in the study of solutions to linear complementarity problem. Linear complementarity problems arise in linear and quadratic programming, computational mechanics, and in the problem of finding equilibrium point of a bimatrix game. M-matrices occur in the study of finite Markov chains in the field of probability theory and operations research like queuing theory. Meanwhile, economists have studied M-matrices in connection with gross sustainability, substitutability, and stability of a general equilibrium to Leontief's input-output analysis in economic systems. The condition of positivity of all principal minors is also known as Hawkins-Simon condition in economic literature. Now let's discuss about the main topic of the presentation, SCHUR complement. In linear algebra and theory of matrices, the SCHUR complement of a block matrix is defined as follows. Suppose P, Q are non-negative integers and suppose A, B, C, D are respectively P cross P, P cross Q, Q cross P and Q cross Q, where the first one are rows and the second one are columns matrices of complex numbers. let M equal to A, B, C, D, where A, B are in rows and C, D and A, C are in columns, so that M is a P plus Q and P plus Q, so that M is a P plus Q by P plus Q matrix. If D is invertible, then the Schur complement of the block D of the matrix M is the P into P matrix, defined by that M by D is equal to A minus B into D inverse into C. If A is invertible, the Schur complement of the block A of the matrix M is the Q by Q matrix, defined by M by A equal to D minus CA inverse into B. In the case that A or D is singular, substituting a generalized inverse for the inverses of M by A and M by D yields the generalized Schur complement. The Schur complement is named after Isai Schur, who used it to prove Schur's lemma, although it had been used previously. Emily Virginia Hainsworth was the first one to call it Schur complement. The Schur complement is a key tool in the fields of numerical analysis, statistics, and matrix analysis. Now let's discuss about the backgrounds. The Schur complement arises when performing a block Gaussian elimination on the matrix M. In order to eliminate the elements below the block diagonal, one multiplies the matrix M by a block lower triangular matrix on the right as follows: M equal to A, B, C, D, which is later converted into A, B, C, D into identity of P matrix, which is 0 and minus D inverse into C, and also IQ, which is equal to, which on being multiplied gives us A minus B D inverse into C, B, 0 and D, where IP denotes P cross P identity matrix. As a result, the Schur complement M by D equal to A minus B into D inverse into C appears in the upper triangle, continuing the elimination process beyond this point, which is performing a block Gauss-Jordan elimination. A minus B into D power minus 1 C, B, 0 D, which is then later multiplied by again the same thing, which is IP minus B into D inverse 0 and IQ, which gives us A minus B into D inverse into C, 0, 0 and D, which is almost the same, and it leads to an LDU decomposition of M, which reads as the following: M equal to A, B, C, D, and which is IP B D inverse 0 IQ into A minus B into D inverse into C, 0, 0 D, and also into IP 0 D inverse C and IQ. Thus, the inverse of M may be expressed involving D inverse and the inverse of Schur's complement, assuming it exists as M inverse equal to A, B, C, D 4x4 matrix, its inverse, which is equal to the equation which was given earlier into its inverse, like IP B D inverse 0 IQ multiplied by A minus B into D inverse C 0, 0 D, which is again multiplied by IP, which is an identity matrix, 0 D inverse C, and the fourth row and the fourth element is IQ, which is the identity matrix, and the whole of its inverse, which is equal to IP 0 minus D inverse into C IQ into A minus B into D inverse into C whole inverse 0, 0 and D inverse, which is also again multiplied by IP minus D into minus B inverse 0 IQ, which is equal to A minus B into D inverse into C whole inverse minus of A minus B D inverse into C whole inverse again multiplied by B into D inverse, and the third one is minus D inverse into C, which is multiplied in brackets with A minus B into D inverse into C, again its whole inverse, and the fourth element is D inverse plus D inverse into C multiplied by A minus B into D inverse into C and its whole inverse into B into D inverse. The above relationships comes from the elimination operations that involve D inverse and M by D. An equivalent derivation can be done with the roles of A and D interchanged. By equating the expressions of M inverse obtained in these two different ways, no one can establish the matrix inversion lemma, which relates to the two SCHUR complements of M is to M by D and M by A. The derivation from LDO decomposition in Woodbury matrix identity and alternative proofs is one of the best references for it. We can later check it out. Now let's get into the properties. If P and Q are both 1, which means A, B, C and D, all the matrices are scalars, we get the familiar formula for the inverse of a 2 by 2 matrix, which is given by M inverse equal to 1 by AD minus BC into D minus B minus C A, provided that AD minus BC is a non-zero. In general, if A is invertible, then the matrix M equal to A, B, C, D equal to IP 0 C into A inverse and IQ, which is multiplied by A 0 0 D minus C into A inverse into B, which is again multiplied by IP A inverse B 0 and IQ. It gives the M inverse as A inverse plus A inverse into B into M by A and its whole inverse, again multiplied by C into A inverse. And the second element is minus A and its inverse into B into M by A and its inverse. And the third one is minus of M by A's inverse into C into A inverse. And the fourth one is M by A inverse. M by A whole inverse. Now when it comes to the SCHUR's formula, when A respectively D is invertible, the determinant of M is also clearly seen to be given by determinant of M equal to determinant of A into determinant of D minus C into A inverse into B, which respectively gives determinant of M is equal to determinant of D determinant of A minus B into D inverse into C, which again generalizes the determinant formula for 2 by 2 matrices. Gutmann rank additivity formula states that if D is invertible, then the rank of the M matrix is given by rank of M equal to rank of D plus rank of A minus B into D inverse into C. Next, Ainsworth inertia additivity formula states that if A is invertible, then the inertia of the block matrix M is equal to the inertia of A plus the inertia of M by A, which is also quotient identity A by B is equal to A by B by C. The SCHUR complement of Laplacian matrix is also a Laplacian matrix. Application to solving linear equations. The SCHUR complement arises naturally in solving a linear system of equations such as A, B, C, D into X and Y is which gives us U, V, which is a column matrix. Assuming that the submatrix A is invertible, we can eliminate X from the equations such as X equal to A inverse into U minus B into Y. Substituting this expression into the second equation yields D minus C into A inverse into B into Y equal to V minus C into A inverse into U. We refer to this as reduced equation obtaining by eliminating X from the original equation. The matrix appearing in the reduced equation is called the SCHUR complement of the block of matrix in the A in M. S equal to, which is definitively positive, D minus C into A inverse into B. Solving the reduced equation, we obtain y equal to S inverse into V minus C into A inverse into U. Substituting this into the first equation yields x equal to A inverse plus A inverse into B into S inverse into C into A inverse into U minus A inverse into B into S inverse into V. Now we can also express the above two equations as a column matrix xy equal to A inverse plus A inverse into B into S inverse into C into A inverse minus A inverse into B into S inverse minus S inverse into C into A inverse, and the last element is S inverse, which is again multiplied by another column matrix, which is of course U and V. Therefore, a formulation for the inverse of block matrix is given by A, B, C, D whole inverse, which is equal to A inverse plus A inverse plus A inverse into B into S inverse into C into A inverse, negative A inverse into B into S inverse, negative S inverse C into A inverse S inverse, which is again equal to IP negative A inverse into B zero IQ A inverse 0 0 S inverse IP 0 negative C into A inverse IQ. In particular, we can see that the SCHUR complement is the inverse of 2 by 2 block entry of the inverse of M. Applications to probability theory and statistics. Suppose the random column vectors x, y live in R power n and R power m respectively. Then the vector x, y in R power n plus m has a multivariate normal distribution whose covariance is a symmetric positive definite matrix. Sigma equal to A, B, B transpose C, where A belongs to real numbers n cross n, n by n, the columns and variances, the columns and rows, is the covariance matrix onto X. C also belongs to the real numbers into m into m, which is the columns and rows again, rows and columns respectively, is the covariance matrix of Y, and B belongs to the R n cross m, where R are rows, where n is rows, where n is number of rows and m is number of columns again, of course, is the covariance matrix between x and y. Then the conditional covariance of x given y is the SCHUR complement of C in sigma. Covariance of x by y is given by A minus B into C inverse into B in transpose, and E into x by y equal to E into x plus B into C inverse into y minus E into y. If you take the matrix sigma about to be not a covariate of a random vector but a sample covariance, then it may have a Wishart distribution. In that case, SCHUR complement of C in sigma is also has the Wishart distribution. Now let's conditions for here are the conditions for positive definiteness and semi-definiteness. Let X be symmetric matrix of real numbers given by X equal to A, B, B transpose and C. Then if A is invertible, then X is positive definite, and only if A is its complement, X by A are both positively definite. X greater than A implies if x is greater than A is greater than 0, x by A is equal to C minus B transpose into A inverse into B, which is again greater than 0. If C is invertible, then X is positively definite, and only if C and its complement X by C are both positively definite. X greater than 0, X is greater than 0 if only if C is greater than 0 and X by C is equal to A minus B into C inverse into B transpose, which is greater than 0. If A is positively definite, then X is positive and semi-definite if and only if the complement X by A is positively semi-definite. If A greater than 0, then X is greater than or equal to 0 if and only if X by A is equal to C minus B transpose into A inverse into B, which is greater than or equal to 0. If C is positively definite, then also the X is positive be semi-definite if and only if the complement x by c is positively semi-definite. If c is greater than 0, then x greater than or equal to 0 is then x is greater than or equal to 0 if and only if x by c is equal to a minus b into c inverse into b transpose, which is greater than or equal to 0. The first and third statements can be derived by using the minimizer of the quantity u power t a into u plus 2 into v transpose u transpose into au plus 2v transpose b transpose u plus v transpose c into v as a function of v for fixed u. Furthermore, since b transpose c is greater than 0 if and only if c b transpose b a is greater than 0, which is kind of a transpose. And similarly for semi-positively definite integers, the matrices are the second and respectively fourth statement is immediate from the first step and the respectively third statement. There is also sufficient and necessary condition for the positively semi-definiteness of x terms of a generalized Schur complement. Precisely, x is greater than or equal to 0 is if and happens if and only if c minus b transpose into a power g into b is greater than or 0 is greater than or less than 0, where I minus a into a power g into b is equal to 0 and x is greater than or equal to 0 happens if and only if c is greater than or equal to 0, a minus b into c power g into b transpose is greater than 0, where also I minus c into c power g into b transpose is also equal to 0, where a power g denotes the generalized inverse of. Here we can conclude the Schur complements of the M matrices. I hope I have given a good presentation. I would like to say 2 words before I end it. Thank you.